Welcome everyone to MSD at Home. We are ready to start. My name is Alberto PUGNALE and I'm a senior lecturer in architectural design at the Faculty of Architecture, Building and Planning here at the University of Melbourne. I would like to begin these proceedings by acknowledging the traditional owners of the many lands on which this event is virtually taking place. I would like to pay my respect to their elders, both past and present, and I extend that respect to other Indigenous Australians present. Today, it's my pleasure to introduce Dr. Alessandro BEGHINI, who has joined us from San Francisco. So welcome, Alessandro. It's also a great pleasure to hear Alessandro's presentation and at the end of the talk to be able to facilitate a Q&A session with you. I'm going to ask to all attendees, should you have a question for Alessandro, please submit it through the chat function that you will find at the bottom of the options here on Zoom, and I will read them at the end of the talk. Now, before we begin, I'll just briefly introduce you, Alessandro. Dr. Alessandro BEGHINI is an associate director and a structural engineer with SOM. He's based in San Francisco. And as a structural engineer, Alessandro works to develop the structural design for both individual projects and project groups. He's also responsible for conducting research within SOM. That's in the field of structural optimization, as well as in the development of innovative methodologies for structural analysis. And to this end, he maintains ongoing collaborations with academic institutions, such as the University of Illinois and Northwestern University. He's also been publishing papers on a variety of structural engineering topics. So I'll be very curious to hear from you how you joined design and research within SOM. I'll leave the stage to you, Alessandro, and welcome again.
All right. Thank you. Thank you for the introduction. I'll be sharing my screen now. So it's a pleasure to be here with you today and to be able to talk a little bit about the engineering of art and architecture. And like Alberto was saying, how do we marry research and technology with design, both in art and in architecture? Before we start, I would like to a little bit talk about some of the design principles that are at the core of the work that we do. The first, probably and foremost, principle is sustainability, sustainable design. The importance of acknowledging climate change and the impact of climate change on our surroundings, right? And so acknowledging that, how we are designed, can we address that issue, right? How do we change the way we think about design to address that concern? Another important principle is the principle of natural forms. There is a natural way that systems organize themselves. And you can see here, for example, in just a very simple, like a queue at the Eiffel Tower in Paris, where people line up at the ticket booth and naturally they form these interesting patterns, right? So this natural form that self-organize. And then material, right? Material and its use. So we're used to see steel and concrete, but what about other materials, non-traditional materials? It could be masonry, it could be glass, it could be wood, but what about ropes? What about, fishnets, right? And we'll see a little bit of it today. There's a very elegant way to take non-traditional material and assemble them, as long as we understand them and we understand their properties and qualities. And collaborations, right? I mean, we come from a tradition within SOM of great collaborators, Fazlur Khan, Bruce Graham, just an example of an architect and an engineer coming together to inspire new groundbreaking design, right? Taking that structural expression through the architecture. So how do we inspire a new interdisciplinary collaboration that extends not only to the structural engineer and the architects, but also to the mechanical engineer, the electrical engineer? How do we advance that dialogue? And then technology, right? Technology has always inspired new design. If we even, go back to the German pavilion of 1967, Frei Otto's work, right? He was working on soap films and soap bubbles, and he was taking those and creating new architecture, which was really inspired by that new technology that was emerging at the time. And then geometry, right? Both architects and engineers meet at this intersection. Geometry is really at an intersection point. How do we define forms and geometries that are efficient, right? Structurally efficient, that minimize the consumption of materials, that are, at the same time represent a design and aesthetics that is beautiful, but obviously that incorporates the natural forms, that incorporates the consideration for sustainable design. So how do we take all these principles and designs and incorporate those in a building? Well, what we have been doing at SOM, and this is part of the research aspect, some of the research aspects that we've been working on, we have been developing tools and technologies, and it's just a list of these tools. Some of them were specifically developed in-house, some of them are commercially available, or some of them were developed in collaboration with the universities, PhD students or master students, through research papers. So, we develop tools and technologies to be able to take these principles that I was talking about and inform new design, inform a design that, could become the inspiration for this new architecture and really new art, but in essence is a tool for collaboration and exploration. And today I was going to just, talk a bit about these tools, but I'm going to talk about them through projects, so actually build projects. So you'll see actually in practice how these get incorporated into the design and how the design flow can take advantage of these tools. And just to make sure we're on the same page regarding the terminology and kind of the philosophy behind these tools, I just want to start from the beginning. I think every single project starts from the same basic point, which is this: a blank sheet of paper, right? Everyone has been there, any professional engineers or any architects has been there. So we always start from a blank sheet of papers, and you could start sketching something, you could start from your inspirations, you could start from the limits and the constraints of the site, but in essence we start from a blank piece of paper. So wouldn't it be great if we have some tools that could fill that blank piece of paper with some information that we could leverage to our advantage? So what I'm talking about is essentially a design domain. So we typically work within a certain boundary, a certain space, right? And we need to fill in that space with a geometry. Say that you want to fill this space, these simple rectangles, with the geometry of a truss, right? So you could take the geometry of the truss and the design of the truss through multiple steps. The first step could be simply defining the topology of the truss. Topology is simply defining the proper connectivity from one member to the next one, right? So what bars connect to what? You don't necessarily specify what the nodal coordinates are. Those are still in flux and could be still established, but at least you define a network of members that connect to each other. So the next step of the optimization and the process of design could be to define the shape optimization, which basically takes those points and that connectivity and assign to those points specific placement in space, right? An XYZ coordinates, like for example, in this example of truss, where you set the work point of that middle at a certain specific location relative to the height. Then, as obviously the last step of the design process would be to go into the size optimization, where basically you take a set geometry and you size the members. As you understand, this is the result of a collaborative process where architect and structural engineer go back and forth in refining the geometry and identifying what's the best geometry to respond to certain constraints and to certain inputs. Could be forces, could be design constraints, a number of items, right? And essentially, the earlier on that dialogue, the conversation happens, and the greater impact on the efficiency of the design. If the dialogue happens only at the end, so only in the sizing exercise, a lot of the advantages and efficiencies and synergies are lost, because the greater synergies are at the very beginning in the definition of a proper topology to the system. So I like to start talking about a project that is close in Australia, and then we'll hop over back to the US in the next project. But starting in Australia, I'd like to talk about this project, 100 Mount Street, which has been completed not too far back in North Sydney, Australia. is 148 meters tall, 35 stories. It's the work was done for Lane O'Rourke. Lane O'Rourke is a contractor, and we've been working with them a lot in the past. And working with a contractor, one of the paramount goals is always efficiency and constructability, right? I mean, they come from the construction side, they want something that is buildable, something that is highly efficient. And what you see here is a view looking from the bottom up of the bracing elevation. And this bracing elevation incorporates some of these ideas of topology optimization that I was talking about, and I'll present in a second. Just to give a little bit of context to the project, you can see it here relative to Sydney in general. So North Sydney is really up on the hills. So what happened is that there are significant wind loads actually acting on the building. In addition to that, being on a hill, there are escarpment effects where there is wind speed higher as the wind blows over the hills and against the building. So a lot of interaction also with the wind tunnel to define the proper design wind pressure. And anyway, large loads that we were definitely designing for from a lateral point of view. Another picture of the elevation, right? And you can see this very unique feature in the bracing elevation where the bracing are not actually crossing as an X, but the work point is a little bit higher up relative to the midpoint. And that's really intentional because of the efficiency considerations that I'll mention in a second. Also, as I said, I mean, the contractor wanted to take advantage of as much as possible of the height, and there were height limitations. And so we tried to squeeze as much as possible the floor-to-floor height. And we came up with 3.75 meters of floor-to-floor, which is pretty tight for our office space. And we were able to achieve that through careful consideration on the way we could define the gravity system for the floor plate. This is a picture of the ground floor that starts highlighting the way the structure was laid out, the structure and the architecture were laid out. First of all, we had to deal with the constraint on the left of 80 Mount Street and existing buildings, right, that was there. And with the goal of maximizing the views from inside the building to the outside, we thought that the best opportunity was to actually place the core right up against on the left to 80 Mount Street. That way, we would have an eccentric core, which is obviously very challenging from a structural engineering point of view. We typically like, you know, the core at the center or relatively centered, but understanding, you know, where the client was coming from, obviously we were receptive to that and we pushed it to the side. That eccentricity though caused us to move to have a very stiff frame on the right, which is the frame that I showed you in the elevation in the previous image. In addition to that, you see a very open ground floor. There's only 10 columns in this building, and they are consistent all the way up, and really to open up as much as possible the spaces and create a lot of flexibilities and definitely beautiful views. If you look at the typical floor plan as you go up, there's the typical high rise and the typical low rise. You can see how the core on the left becomes even further eroded and further eccentric as you go at the upper level, because your core essentially becomes a C, which is really an extreme eccentricity if you think about it. And at the same time, you can see those minimal gravity columns that are there. They are really absolutely as small as we could possibly make it to open up as much as possible the space. I mentioned earlier that one of the challenges was the very compact floor-to-floor height, the 3.75. That pushed us to really look carefully at the natural flow forces and really the bending moment diagram across the span. First of all, the spans are pretty significant. You can see here, we're talking about 17 meters in the clear span at the center and 6.5 meters cantilevers. So we leveraged a post-tension system with PT beams on the column lines. And in addition to that, we shaped the beam to reflect the moment diagram in order to be able to be as efficient really as possible in the way we were using the material. And essentially having notches, I mean, you can see how it comes back up, the beam profile, where we have the point of low stress. And we leveraged that from a mechanical point of view to put the ducts on those locations, so that our soffit, our ceiling, was as compact as it could possibly be, because basically we're really leveraging the synergies between the mechanical system, the structural system, and the architectural design intent in a way that comes all together. Once you start building it, you can see here a picture. It's really quite beautiful to see how these post-tension beam actually reflect perfectly that moment diagram, and you have these returns in the middle, and also you can see on the right that pretty relatively shallow cantilever beam considering the size of that span. Eventually, a ceiling is put up and you don't see all the beauty of the structural system. However, you still have a very efficient system. You see the ducts that start coming up. I'm going to point at them. You see the duct here that start coming up in the ceiling, and then it will be eventually completely covered. And these are the views. This is a picture. This is not a rendering. It's the beautiful view of Sydney from the inside that is really possible thanks to this opening up of the floor plan as much as possible and leveraging these structural efficiencies. After talking about the gravity system, let's switch gear here and talk a little bit about the lateral system. As I mentioned, the lateral system is an expression of the application of structural topology optimization techniques in order to identify the optimal geometry of the bracing. In the next slide, I'm going to show you a structural optimization software run, where basically the software, this is a commercial software we use, the software redistributes the material within the design domain to achieve the stiffest frame possible for a given load that is applied to the building. These are wind loads we are contending with, very high wind loads, as I mentioned earlier. You can see here the redistribution. It was going to cycle through it, but you can see there are blue zones where basically you can remove material and you don't need material, and red zones where the material demand is really, really high. If we take just a few stills, here are the stills of the the sequence of the analysis. You can see the different steps. So this was just a conceptual study that we did, and when we saw emerging these patterns, this high brace point and not just a simple X, we were really questioning the numerical results. And this is part of also of the design process and the research process. Is a part of it is looking at the research results or the numerical results and questioning them and really investigating if those are real or is just there's something that is off in our assumption or in the parameters or in the analysis. And so we like to do hand calculations. So on the left here, we have some hand calculations that we did in order to convince ourselves that actually the results was correct. And it is indeed correct. And the reason why that point wants to be a little bit higher is because once you have, say, that single square module here on the top right, when you apply a load at the top, there is a balance between a shear load and an overturning moment, right? If it was a pure shear load, perfect, the X would be a perfect answer to it. However, the presence of the overturning moment upset that balance so that the work point really wants to be a little bit higher up. And there's actually a clear proportions where it wants to be 3/4 of the height up relative to the module. So we were able to take those research results and analysis and incorporate them into the design, right? And a lot of work was placed into conceiving the optimal geometry, but also a lot of work was spent in the proper detailing. So there is also, the next step in the constructability consideration that go into the design of the system. And just, I want to point out one of the main connection is the connection that really links together these two braces. And, sometimes, there's multiple considerations that go into it. In addition to wind loads, there is going to be creep and shrinkage, there is temperature. So there is a lot of demands. And one of the unique aspects of these projects is that the demand on that center node, actually there was a significant horizontal force due to the creep and shrinkage and temperature effects. They were so high that we decided to actually let the connection in the middle breathe and allow them to slide relative to each other so that they are linked vertically for the shear that needs to be resisted by wind load, but they can actually slide relative to each other. So you can see here in the exploded view how we introduce those elastomeric pads in order to allow for that sliding connection into the system. So from the very conception until the end, there's a lot of detailing work that is required to take an initial idea or a design efficiency or a structural optimization efficiency into reality through the proper detailing. And the result is a beautiful, obviously, beautiful example of architecture and structure integrated into the building. We have a couple of more projects coming up in Australia. One is in Sydney. Central Place is a collaboration with Fender Castalidis, and is really to revitalize the center business district. It's a mixed-use project with the 2 towers, 37 to 39 stories. And so if you want to follow the developments of that, you can look at those online. Another project in Melbourne, 600 Lonsdale. This is another mixed-use tower. It's about 42-story building, and is also upcoming in Australia. So, 100 Mount Street was a great example of application of research to the overall design of the tower. So it was very apparent, the geometry of the bracing on the perimeter of the building. But, these techniques are applicable even at the component level, even in elements that are not really visible to the outside. This next example in Los Angeles, California, so we're crossing the Pacific here, is the new federal courthouse, which employed similar techniques, but is not so apparent from the outside. The building is right downtown, is a great location just by the Opera House in the back, and is essentially a suspended cube. It's literally at 230 feet by 230 feet by 230 feet. It's essentially a cube. And you can see at the bottom of the building, is actually notched back. The design intent here was that the perimeter columns would not touch the ground. There were several considerations for it, concerns about threat. This is a government building. Our client was the General Service Administration. And so because of these concerns, they decided that the best solution was just to not have any column touch the ground and basically have a setback of about 36 feet, which is a cantilever of about 12 meters. So a very significant cantilevers. So if you look at the floor plan, an architectural floor plan, essentially we have 4 cores, right? At those locations, those are going to be reinforced concrete cores, where we have the stairs and elevators. And a lot of coordination was in place with the architectural team and the MEP team in order to be able to achieve the optimal efficiency of all the different spaces. The aspects that I want to look at closely, though, is really how the structural system was informed by these research technologies I mentioned. And in essence, we have these reinforced concrete shear walls, which are the whole lateral system for the building. All the load that is coming from this system of perimeter steel columns, all these columns are hanger columns. They're hanging from a roof truss that then connects back into these reinforced concrete shear walls. In addition, we had a perimeter moment frame in order to increase the redundancy of our load path and obviously increase the possible resistance against accidental or unpredictable loads, let's say. Here we are with a moment frame on the left, as I mentioned, on the perimeter of the building. And you can see here the setbacks at the bottom that creates these notches. And these notches are 36 feet, so 12 meters is a very significant span. So if you can imagine, here is just a 3D view. All the perimeter is really going up to the top, where we have this three-dimensional 3D space truss, and then back down towards to the core wall. So the red arrows are showing the load path as it's coming up from the perimeters through the truss back down. So a lot of time was spent to understand how this cantilever was going to work and how the research tools we developed could help define the right geometry for the truss, accounting for all the constraints that were in place, because this was still a usable space. There still has to be some way of getting in and out of there, and therefore all these considerations had to be taken into account. So you can see here on the left, the same analysis, the same software using topology optimization and material redistribution is done on the left. And you can see here we started incorporating some of the constraints. We have here a door that needed to be placed, and you can see how the material redistributes around that door. So the solution also needs to acknowledge all the possible constraints and limitations that are in place. On the right, you see how this geometry progressively came into place, and obviously is also reminiscent of the so-called Mitchell trusses. Mitchell actually was an Australian mathematician who wrote a very important paper in 1904 on the most optimal, the stiffest trusses for least weight. And you can see that the bicycle wheel geometry is actually one of these trusses, and the geometry we came up for that cantilever portion of the truss is actually very close to it. Eventually, you can see here, we came up with an optimal geometry, which is the dashed black line. We decided for constructability reasons and other rationales to go with the red dashed line. However, there's an important point to be made that once you identify what the absolute optimum has to be, and you deviate from it, is usually the inefficiencies are very small. Let's say in the order of 4 or 5% more inefficient. However, if you start from a point or a geometry that is really not efficient at all, or it doesn't incorporate any thoughts for optimality, it's going to be very hard to optimize it. Basically, there's no opportunity to do any optimizations other than the size, the sizing exercise I mentioned at the beginning. So adjusting from a point of optimality is still fine, and there is plenty of design opportunities around that point. So here is a comparison between where we started at the top, which is a simple moment diagram type of solution, to the bottom where we have the bicycle wheel that allowed us to save about 14% reduction in weight. So less use of resources and obviously much more efficient structure. This is during construction. This was taken. You can clearly see the load path, how it comes in reality. And you can see that the truss actually dives down on the lower level. And that was possible because, again, coordinating with the architecture, there was space in the soffit of that specific space. So everything was considered holistically from a design perspective with our with the design team. There's a lot of things that we can say also about this truss. Actually, we are in LA, high seismicity, and therefore we had to introduce buckling restraint braces in order to be able to control the interstory drift. So if you actually continue this bicycle, the bicycle continue right here with the buckling restraint brace. I'm going to show you here in a second. So you can see here the geometry of the buckling restraint brace up at the top. So there is a lot more, again, to this project beyond the aspects, the more research or design, the structural optimization aspects that has to do, with the loadings and the site. So buckling restraint braces really linking these cores at the top and ensuring that basically the interstory drift was relatively uniform within the building and connecting them at that level and helping dissipating energy, given obviously the large earthquake that we were designing for. Down obviously to the detailing, these connections of these three-dimensional space truss obviously are relatively complex and require careful coordination with the fabricator. So going down to obviously the details of the welds and the bolts and all the different aspects of the construction. Eventually, this is one of my favorite pictures of the construction. The curtain wall is not up yet. You can still see the trusses, right? Eventually, they were covered up, but it's still a beautiful example of collaboration, interdisciplinary collaboration and application of these optimization tools to come up with a very logical rationale for efficiency in the structural system. The next project I want to talk a little bit about also the collaboration we have with artists. So we've been working with artists for a long time, on and off, right? It even goes back, if you see here, to the work we've been doing with Picasso, Pablo Picasso, with the Chicago Picasso in many years ago. And working with artists is very interesting because it's a very interesting interaction. Artists are open to pioneer new technologies. They're open to really finding new materials, applying new forms, and they really bring a fresh perspective in the design process. And they're open, they often challenge the engineer on the opportunities that are available to them in order to express their design or their vision. And so today I just want to talk about this collaboration we have with Janet Heckelman. Janet, we've been working with Janet for a long time now. I'm going to talk about this project we did with her in West Hollywood. So we're still in the LA area, but West Hollywood, California. The project is called Dreamcatcher. And this is a picture of the Dreamcatcher looking from below, looking up. Is a very colorful floating sculpture that spans about 30 meters or so between two hotel towers. So on the side of this picture, you see these two hotel towers. The project is located in the heart of West Hollywood. It's Sunset Boulevard and La Cienega. So it's really a great location. It's up in the hills, and you can have beautiful views of LA. And as part of we were the engineers and architects of record for the project. So as part of the project, there was the requirement of a permanent public art installation. And so Janet was called for this. And so we started working with her on the project, and it really turned into a beautiful piece of art that is strung between these two sculptures. And all these are pictures. There's no renderings here. They're all pictures. It's lit up at night. It really energized the place. It really energizes this plaza and all the occupants of the two buildings. And I remember when Janet came to us with this project, she didn't really know what the project was going to be about, but she knew that it was going to be about dreams, and she wanted it to be a dream catcher. And so, sure enough, as engineers in our ingenuity, we just Googled it. We just went in and Googled Dreamcatcher, and you'll see you have plenty of images, all this iconography of a dreamcatcher, literally in this image here on the top left. And then from that geometry, what we did in essence, we kind of simplified it, and we looked, at simplifying a little bit the geometry, and then we applied form finding techniques. It's called the force density method. We applied the force density method to adapt that geometry to the site. And that's the result of it, right? This is just a construction drawing below of that geometry. The way the piece is organized in layers. There's 4 layers, okay, of what we call structural nets. And in between the structural nets, there is sculptural nets. The sculptural nets are fishnet type material. It's very colorful. I can just show you 1 second. You can see here in the picture on the right here, these white lines are the structural nets. Those are ropes. That's a structural rope material. And the colorful material here is actually fishnet material, which is made with the same technique of a fishnet, or a net for a goal or for any other application. So as you can imagine, as a structural engineer working with ropes, I mean, at the beginning, we had no idea what we were dealing with. So we did a lot of testing. So you can see here on the left, some of the testing that we did on the ropes to understand their behavior. And the behavior is highly nonlinear. If you imagine when you pull on a rope, at the beginning, you can pull with very little force, you can get a lot of stretch. But then at some point, right, there is a bedding in the rope, and then you start catching more and more, and it requires a lot more force to pull on it. So the behavior is what is called highly nonlinear from a material standpoint. And is also the displacement of these sculptures are very large. You're talking about meters and meters of displacement, because they're supposed to move, right, in the wind. So it presented a lot of numerical challenges of analysis. There's also a picture here at the fabrication facility on the top right. Basically, this is on the floor of the fabrication facility. When it's pulled down on the floor, it doesn't look like just a bunch of spaghetti there lying, but then it gets pulled into a box, it gets shipped to the site, and then we pull, the installer pulls on them at the corners, it eventually comes in place as the design piece. There's also a lot of craft in place because all the rope splices are done by hand. So there is a lot of interesting fabrication methods that comes into place, and a lot of crafting. There's a couple of images of the analysis that was conducted for the piece, just to highlight the challenges, as I said, from a numerical point of view, not only form finding, but also analyzing what would happen in the case of a wind event, right? This very, very large displacement that occurs. And because we were pushing the limit so much, we decided that we also needed to do some verification by physical modeling. So we took some of the form found shape that we had, and we tested them with scaled models, quarter scale models of all these forms in order to confirm our assumptions. Eventually, like I said, this gets shipped to the site, and careful consideration needs to be placed also on the construction sequence, because we have 4 layers of structural ropes that it needs to be taught. They have to be taught in the proper sequence, right? We don't want to tension one layer all the way, because it would be hanging, right? All the fishnet would be acting as a tie between multiple layers. And so they wouldn't be performing as structurally we wanted them to. And therefore, it's a lot of relocation of those tensioning devices. You can see here a picture during the installation. And so it happened over a course of a week to 10 days. I mean, the whole process of tensioning this piece. And obviously also a lot of care was placed into the detailing. So one of the advantages of being the engineer of record for the building is that we were designing the building as we were designing the sculpture. So we were able to go in early on, and this is, you can see the picture on the right here, where essentially we were able to embed some steel boxes in the slab before casting. This is an 8-inch PT slab. We were able to place those boxes so that, as you can see here on the top left, the connection of the sculpture goes through a flute that is embedded in the slab back to this plate here, and it just gets locked in, right? So it's a seamless transition from the sculpture through the slab back to this plate. So it's really beautiful integration of art, architecture, and engineering through obviously careful consideration and careful collaborations with the team. And the result obviously is really beautiful. Like I said, again, a couple more pictures here. Is lit up at night, and the light changed color during the night. And so depending upon the time you're there, I mean, it could be a totally different impression. And also it depends on if there's wind, if there's a breeze, is even more beautiful. And when we start working with an artist, typically we have multiple collaborations with Janet in particular. We've been working a couple more pieces, and we have a few more pieces in the making. On the left here, a piece we did for the Peninsula Hotel in Hong Kong, and on the right, a piece that we did for a project in South Korea. This leads me to the last portion of the discussion, and I want to just give you a sneak peek on what we think is the future of art and architecture. And oftentimes, the opportunity to look into the future is given by the exhibitions, the traveling exhibitions. So we've been organizing since maybe 2015 or so, structural exhibitions around the world to share our structural work and our structural knowledge with the general public. And the structural exhibitions over time became an opportunity to really push the envelope of what our research is about, and really get into fabrication and really build small prototypes that showcase technologies. An example of it, for example, for the exhibition that we did in 2018 at the MEC Center for Art and Architecture, we built this kinematic pavilion. The kinematic pavilion is a movable pavilion. It's actually, you can morph it. It's essentially based on the theory of rigid origami. And you can actually move it easily. Two people can change the form of it. And we fabricated it, and it's an opportunity also for us to get our hands dirty and really test some of these ideas. 2019, the following year, we did an exhibition in Madrid and worked on timber vaults. So we partnered up with the University of Alcalá and the Timber Vault workshop to build this 5 meters by 5 meters by 3 meters tall vault, timber vault. And timber vault technology is interesting because these are very, very thin vaults. They became famous in the world because of the work of Guastavino. Guastavino used to build these type of structures and vaulted structures, especially in New York. And essentially are vaulted, you don't need any scaffolding, okay? They're self-supporting systems, right? And so it was a very intriguing idea to be able to build this kind of vault. And sure enough, in 2020, we took our knowledge from 2018 and 2019 to London in the UK for this exhibition, The Anatomy of Structure, where we pushed our ambitions to the next level. What we envisioned for these exhibitions that happened this year, right before COVID-19 started, and unfortunately, we had to step back in the operation of the exhibitions. But in essence, what we did, we took what we learned, and we set certain goals, right? We wanted that the new project to be about automated construction, so robotic constructions. How can a robot helps in the construction of systems, right? Not only that, what we learned from the VALLT project from the previous year is that the masons were using guides, okay, to lay out the brickwork. The brickwork itself doesn't need false work, but they need guides because, as you can imagine, when you're in space, right, one thing is to look at your model in Rhino. Another thing is you're building a vault and you need a visual guide to be able to see where you're going, right? And so there were these visual guides, literally, that were built essentially just for them to interpolate between the guides visually as they were going. So it's a very artistic type of work. It was impressive. So we didn't want to use any false work. We didn't want to use any guides. And also we wanted to use standardized size bricks. So we noticed that, you know, the field cutting of the unique shapes that were in some of the corners of the doubly curved vault, the timber vault, were time consuming. So we said, what if we limit ourselves to one brick size or two? And how can we work with that to, you know, build the next generation of vault or structure? And also we use our research tools, and we wanted it to be a display of the so-called Aristotle function theory. The Aristotle function is an approach to design where you're designing a vault or a curved structure actually using forces rather than geometry. So you actually define the forces that you want to see in your shell, and you describe them using a function, and then taking that function, you can derive the form. So it's basically designing by force rather than by geometry. It's a very interesting approach. Sure enough, talking about robots, obviously we weren't experts at robotics, and so we partnered up with with a number of colleagues. We work with the university, with Princeton University, the CREATE Lab and Form Finding Lab with Stefano Parashko and Sigrid Adriansen. And also we worked with Global Robots. They provided the robots for the exhibition, with TU Delft for the connection between the bricks. Poesia Glass Studio provided the bricks. And also Ambika Gallery and the University of Westminster helped with the development of the concept. From the very beginning of the project, there was the idea that we wanted to showcase how two robots could work together collaboratively, right? So there is a collaborative space where the two robots work together, and then there is an individual space where the robots can work. Not only that, but we were fascinated by the idea of blending modern technologies with older technologies, right? And so actually we came across this book by Hyman, the stone skeleton, which describes ancient, very old Byzantine or Assyrian era construction of barrel vaults, and how they were able to build them in essence, as described in these pictures. We use the technology on the right here, where basically if you have a vertical wall, you can use the vertical wall as a permanent formwork. And essentially you're building the barrel vault as a series of leaning arches, okay, that come from the vertical wall. And so the idea was that maybe the robots could work together to build a center arch, right? And then from there, we could build a series of leaning arches coming out of that center arch. Similarly to this very antique technology. As already mentioned, the way we approached from a design point of view, the definition of the form was the Aristotle function, which is an approach that allows you to define the forces and work with the forces rather than with the geometry. And, you know, working with robots obviously affects the way you think about design. So inevitably, it's a back and forth between, okay, what is the design domain that we're working with and what are the constraints that we're working with? So if you have two robots that are set at a certain distance, first of all, those robots have a certain reach. So this circle describes the reach of the robots, how far they can go. And also keep in mind that these robots are moving, and because of their articulation, a careful planning of the path, you know, of the movement of the robot has to be considered. And if you think about, for example, the elbow of the robot could not be in conflict with the vault itself. So we had a number of constraints that led us to consider the design very carefully for all these constraints when all these constraints were put in place. So naturally, the form ended up to be asymmetric. And it's not asymmetric because we liked it asymmetric. It's asymmetric because it had to be asymmetric because of that constraint, right? But you know, at the end, it was really a quite elegant, interesting form that incorporated all these requirements that were provided from the onset This is just a three-dimensional form. And so we worked with this geometry. We did a lot of analysis on it and studies. Material, as I mentioned at the beginning, we need to explore more materials other than the traditional materials. And we were really inspired by this sculpture. This is a sculpture by White at the 2017 Venice Biennale. This undulating sculpture of glass blocks, which is really quite beautiful. And so we asked ourselves, why don't we use glass as a construction material? Glass, you know, really is very strong in compression. The tensile capacity is not great, but you know, we could leverage the Airy stress function to have a compression-only shell, and therefore, I mean, it was a perfect application. And so, you know, these are just a couple of the samples that we were looking of glass. There's purely transparent glass, and then there is the not transparent glass on the right. We ended up using. Once we knew the material, we knew the shape, a lot of time was spent in the tessellation. So once you limit yourself to just 2 brick sizes, we were using a full brick or half brick, right? And we had to limit the gaps between the bricks to be between 6 millimeter and 30 millimeter, right? We didn't want them to be, they couldn't be 0 because there is a tolerance to the movement of the robots, and they couldn't be too big because otherwise it's just unsightly from a design perspective. So a lot of time was spent in the tessellation once you put in those constraints, but we were able, as you can see here, to identify the proper tessellation for the project. So in essence, the construction sequence you can see here, as I mentioned at the beginning, the robots on the left work together to build an arch, which is the center arch. And then after they build the center arch together, each individually continues building the vault on the other side. A lot of testing and prototyping had to be done. This is one of my favorite pictures. This is a picture at the Princeton lab of the 2 robots working together to build that center arch, right? And as you can imagine, the robots alone needs to be able to pick up the thrust that is coming from the full arch. And these are glass bricks, so it's a pretty significant load that it needs to pick up, right? And you can imagine the most critical point was really at this stage when one robot is holding, the other one needs to lose the grip in order to go and pick up the next brick. And obviously, a lot of attention was paid to this phase. This was the most critical phase of any one of our tests. Eventually, the test of principle were very successful. You can see here, we built a full-scale mock-up of half of the vault. We used a mixture of glass and concrete here, just because glass bricks are quite expensive, and so we casted some concrete bricks. And again, as someone in our New York office spent the weekend in Princeton casting concrete bricks, so it's really a hands-on type of experience, which is really a great learning experience. So from Princeton, then the team went to London. This is the setup in London. Whenever you go to the actual site, there's always things that are unexpected or they don't work out, and certain of the some assumptions that you thought were figured out, they weren't, and it's just a learning process. But we were able to streamline all the issues that came up at the site, set up the robots, get them calibrated properly, and then we were able to start the construction. This is a picture, of the glass vault towards the end of the construction itself. And it's really quite beautiful. The material really, looking at it up close, is really, the use of glass is really quite beautiful in this application. And it was very interesting, it was very interesting to see how robots can really help, the construction. And in this case, we really leveraged the ability of the robots to be able to place something in space very precisely, right? Very, very accurately. But at the same time, there was a human component. Humans are very good in on-time adjustments. So for example, it was hard to predict the exact gap that there would be between 2 glass bricks. And that's where the human component would come in place. So it was really an interaction, a human-robot interaction, the construction of this vault, a really great learning experience. We have a very short video, just a 1 minute, couple of minutes video. T, if you don't mind, I'm going to stop sharing. If you can just play the video that we put together for this specific project, which kind of summarizes this workflow, and then I think we can open it up for question after this. T, can you? So this video, by the way, is available, and we published several articles online on the on these glass vaults and how it really came into place. And it is really an exploration on the this interaction, you know, where robots comes in place and where humans come in place. A lot of the people you're going to see in this video are actually students, Princeton University students that worked on it from the very beginning. And this is the example, the Guastavino vaults that I mentioned at the beginning, those timbral vaults. There's some beautiful examples. And, you know, there's been a lot of prototyping and in order to settle on a specific tessellation. You can see here some of those connections and some of those gaps was really challenging to find the right balance between the minimum and the maximum gap. And yeah, Poesia Glass Studio was our partner. They also have other projects that they worked on, fully glass facades, very beautiful. A lot of planning and coding to properly define the path for the robots. You can see here the connection. I didn't talk a lot about connections, but these connections are made up with epoxy. So it's a rapid setting epoxy that is placed in those spaces because it could make up differences. There were tolerances we were dealing with of a few millimeters. So it was not really possible to have a predefined or pre-cut. It would have been very inefficient to define pre-cut wedges or other type of connection without it being fully adaptable. With that, I'm gonna go back to my screen here, and yeah, I would just like to conclude, you know, the talk. Thank you for the time and the opportunity to speak here tonight, and I'll turn it to Alberto for the questions.
Thank you very much, Alessandro, for the presentation. It was very, very inspiring. I knew when I was going to invite you that, you know, you would touch on the relationship between architecture and engineering, design and construction, virtual and real. And I really enjoyed that you actually started your presentation by doing that, find all the possible different intersections from, you know, geometry, structure, materials, and how those sort of things have been put in practice within SOM. It's also good that in a large firm like yours, there is quite a research component that gets somehow transferred to actual projects. So I remember that, like when I first met you 13 years ago, there was a group in Chicago, the Black Box, that was primarily working on that. And I remember Bill Baker was there in Chicago. I'm wondering how research is conducted right now within SOM.
Right now we are in a period of transition where we are reorganizing a little bit the efforts. I think, you know, I studied at SOM many years ago, and we started off with Bill Baker. You mentioned it was a great supporter of the research, the structural research effort, right? So there is different type of research that we are conducting based on different interests, right, of different groups that we had. So you mentioned the black box, and the black box is highly is focused in computational geometry and fabrication, a lot of digital fabrication focus, right? And for example, from our perspective, structural engineering, it was a little bit more focused on structural engineering topics like efficiency of geometry of frame trusses or optimal shape of roofs, right? And so we developed within the structural group our own research group. But in essence, there were these several entities, right, that were kind of working independently, but together, right? So it's like, you know, I always think of it like Venn diagrams, right? there is like one group, and then there is another group, and then there's something at the intersection of all of these, right? And the black box was kind of an intersection of all these different type of research that has been conducted over the years. And so a lot of this research would feed into the black box, which would then incorporate it into the digital design, right? And it's really also the way we run a project where you have like a digital design expert, right, that can build a digital design model of a tower that incorporates the structural system, exterior wall, glazing, right? There's multiple layers, and so you have to be at the intersection of different disciplines. So a lot of the research has been conducted over the years, like I said, independently but together, right? And right now we're at a phase where this, is more and more blended, right? These boundaries are much more blended because a lot of, for example, of what I showed is really at the boundary, of fabrication, engineering, architecture. It has to be looked at holistically, right, relative to everything else. So I think we are really in a process of blending more these boundaries and reorganizing our efforts.
Thanks, Alessandro. Just following up on this question, we have a student from Georgia Tech asking something along the same lines, but they're wondering, what's the main difference between conducting research within SOM and at the university? And I know you've been involved in both fields. I mean, is there any, from a student perspective, is there any difference between, getting involved in industry research or in academic research?
Yeah, I think, I've been on both, like you said. So I've seen both sides of, I did research, for my master's thesis, PhD, and so I've seen both sides. I think, the research in interesting is, I feel it more, to me, is more fulfilling to me personally. It is because, you have very concrete problems, very real problems, and you see several aspects of a project, and you have the opportunity to develop, tools and techniques that can, really shape an entire structure, right? Like I mentioned in the previous examples, 100 Mousetrade or any one of the projects I mentioned today, the research is much more applied. So there is the theoretical research, which is fantastic, is absolutely important and is key, and it can be can have a huge impact on design. But being within the industry, you can always blend a little bit your position and be in between academia and the industry. I think that's where the most influential position is just being maybe at the intersection of the two, where you really can take what's developed within an academic environment. And a lot of the tools, like Polytop and I don't know, Georgia Tech, Professor Paulino is a Georgia Tech, but we had a long collaboration with Professor Paulino over the years, and a lot of the results I've shown and was developed in conjunction with him and with his students, right? A lot of his students, they came and they did, internship with us. So I think the industry and university, they need each other. I don't think there is really like a separation between the two. I think they need to work together.
Yeah, that's right. I tend to agree with you. I think we're trying to do the same here in Melbourne as much as we can. But, sometimes industry runs at a different pace. So that's generally the main hurdle that we have to deal with. Of course, we've got a lot of other comments, like an architect, a colleague from here, is saying excellent presentation and beautiful project. So he's thanking you once again for the presentation. I know Carlos has worked on high-rise buildings, so it must have been interesting for that. Another question is, you mentioned exploring other materials other than the typical. What materials have you found or used that can be called the upcoming materials for the future? And I guess regardless of the building typology.
Yeah. I think we are still at the beginning. At least that's what I'm speaking for myself. I think I'm still at the beginning of learning more and more about materials. You know, I come from, you know, more traditional concrete, steel, masonry, wood, but now, you know, looking at glass, looking at ropes. I'm really interested in composites. You know, I when I was doing my PhD, I did a lot of work on composites and sandwich composites, and I really see that lightweight materials are really probably the way of the future. There are applications out there, for example, composites, but they're in the civil industry, but they're very limited. Or also, you know, it's not only material, but also techniques. You know, there's a way of redefining what's possible. Like, for example, we just started looking into flexible formwork. I don't know if you're familiar with these techniques, but there is a way to use even traditional materials, but in a different way, looking at them differently, right? Or even looking at textiles, right? Looking at fabric. I think especially from the perspective of being involved in looking at ropes, I was surprised by how strong these rope materials are. Because, you know, a rope, you know, say a 2-inch diameter rope has the same capacity as a 2-inch diameter steel cable. So it's impressive.
Wow, that's impressive.
It is impressive. I was surprised. And it's much lighter. Is, you know, I don't know, 20 times lighter or something. I mean, it's just unbelievable. The problem is that, you know, when you start dealing with ropes, you have, you know, a highly nonlinear material. Steel is very reliable. It's a linear material. You know what to expect. But ropes, I mean, their stiffness is very unreliable. They have creep, relaxation. There's a lot of other concerns that are really unknown. But I think in the field of fibers, there is a whole, I think it's just unbelievable what we can find between fibers and composites material for the future, definitely.
Yeah, I think that's a great answer, but also that you said, you know, it's not only about new materials, it's also about reinventing techniques that have been used in the past, and perhaps it's about reusing the same materials in a different way. I think that, you know, the last few slides in particular that you presented were probably towards that direction, which is, it's also another promising research direction, in my opinion. I'm going to ask you a question from one of our students. It was a student of mine. He's very theoretical and sometimes can put you in a different challenging situation. So this student is concerned about contemporary architectural practice that is generally privileging image over emotion. But it seems in your projects that you presented today, that emotion is still very present within elegant and efficient works of structural engineering. So he wants you to comment on the role of emotion in the design process. Is present from the blank piece of paper that you showed at the beginning, or does it emerge only at a certain point of a project's resolution? So I think the relationship was between image and over emotion. That presence of the image is the, you know, most important thing. How much emotion is there in the projects, and where does it get in?
Yeah, well, I mean, there's a lot of, you mean emotion like passion, like or emotion like inspiration?
I would say it could be a little bit of both. There are probably many ways to interpret emotion, and I know that this is probably a question we should be asking also the architecture team. But
I think there's always, I think working with both architect and artist, well, first of all, there's a lot of passion, I can tell you that. There's a lot of passion, and all the people I've been working with, they're very passionate people, and they're also, you know, they're people that, you know, they never ever give up in the sense that, you know, if you can imagine, like the glass vault example, right? It's there was an inspiration there. You know, there's a lot of emotion because we are inspired by what we see that is beautiful. Like, for example, the sculpture by White, the glass sculpture, the undulating glass sculpture, the Venice Biennale, which was the inspiration for using glass bricks for the glass vault, right? That's a beautiful sculpture. We're inspired by that, as well as we are inspired by nature, right? And the use of natural form as much as possible, because of oftentimes, you know, optimality is already around us. It's not that, you know, nature is optimal by default because there is no other constraints, right? And so it's completely unencumbered and, you know, without any restraints. I mean, it grows naturally as optimal. So there's a lot of inspiration that comes from what we see around us, and it's really surprising, you know, where the inspiration could come from. You know, it could come from anything, really. And working with artists is the same. There is this image, or there is this idea, there is this emotion about a place, about a time, or about, you know, a particular, you know, about the vernacular sometimes, right? Think about the dream catcher and Janet's idea that, you know, okay, it's Hollywood. The project is going to be in West Hollywood. That's a place of dreams, right? So why don't we make it about the dream catcher, right? It's also, there is a hotel there, so the you know, the hotel guests dreaming while sleeping, right? And how this actually dream catcher, you know, the inspiration is really that the structural nets are really catching the dreams, and those fish nets are the dreams, right? So there is a very there's always a beautiful metaphor and inspirations that goes with the project. There's a lot of emotions, and the best projects are the one where those emotions or those inspirations align with also something that naturally comes out structurally because of that, right? If you can marry the two, then those are the most successful projects usually. And that's the reason why I really like the Dreamcatcher, because that image, together with, you know, the structural, you know, efficiency of the system that we have in place, and the materials, definitely incorporates all those into one.
Yeah, I agree. I mean, it's, in a way, it's so fascinating to see how the, you know, the structural team within SOM is so open to work with artists and architects and always explore. It's been open for generations to explore new solutions to problems. I'm just moving forward because we have a couple of extra questions from, we have one from a structural engineering undergraduate student. So they're interested in a couple of things. Of course, they're all thanking you for the wonderful presentation. So in the Mount Street project, what was the software that was used for the topology optimization, and would that software be available to the general public for experimentation?
Okay, so the software that was used is the commercial software is called Altair OptiStruct. Is Hypermesh. Altair is a company. OptiStruct is a commercial software that we have available. It might be available for students. I'm guessing they have like a student or university license they can give you. Otherwise, we also been using successfully a lot of other university software, free software out there, like Polytop, which was developed by Professor Paulino at Georgia Tech. There is the more basic is the MATLAB code is called the 88 or the 99 line MATLAB code for topology optimization by Professor Sigmund in Denmark, DTU, Denmark Technical University. So those are free software and they run with MATLAB. And if you're just, you know, you're really exploring, not at, you know, at super complex level, there are plenty. Because they're MATLAB codes, you just download them and you can start playing with it and just see. But I'm sure they're also OptiStruct. They might have, you know, some special agreements with universities.
And well, with topology optimization, we might also have, you know, some stuff here at our, you know, colleagues at RMIT, Mike Sheehan, ISO, BESO, and those software there. So there are a lot of options around.
Yeah. And you know, there is there's a whole presentation that one could have about talking about these tools, but there's also, ground optimization that you could use. I mean, topology optimization is just one. There's a number of other ways to optimize a structure. You could use the ground structure optimization, is called, where you start with a system of bars and you optimize relative to the bars. So there's really a whole field. And if you're interested in publication, you can, we published a lot of papers. We have a lot of papers in the Journal of Structural and Multidisciplinary Optimization. It's called JSMO. So you can if you just look up my name. If you're at the university, you can probably get the papers, I think, from the library.
Yeah, we are subscribed to most of them,
Yeah.
and I don't know whether this student is from here, but most university will have a subscriptions probably. And one of the other questions that I'm getting, I think these are difficult ones to answer, to be honest. The same student is asking, how do you optimize in general? How do you get into structural optimization? You can be a structural engineer, but not many structural engineers work in optimization. So,
I mean, usually it's like I said, a passion is a lot of, and personal interest is a big part of it. The fact that you're interested in something, it just triggers the fact you're going to look more into it, or at least that's what I think. It's I didn't know about topology optimization when I started at SOM. Honestly, my background actually, my PhD was in theoretical mechanics. It wasn't actually structural engineering. It was theoretical and applied mechanics. So it was, pretty theoretical. And but I studied sandwich composites and constitutive modeling of material, but I didn't know anything about topology optimization. But then, we came across it. I think it was at a conference. One of the, by participating in conferences like the IASS and, these events, you see presentations and you start saying, well, this is something, that could be interesting to me, or it could be relevant to what you do or what your interests are, right? And one thing leads to another one. I wouldn't say it's mostly in personal interest, and quite frankly, honestly, working at SOM, no one ever told me you shouldn't be doing this, or you just have this interest and you see, oh, you could do this, and that. You take this tool and you come up with this incredible geometry. It's it's no one is stopping you from doing it, and just cultivating your personal interest and your expertise over time.
and one of the few good things about being at home in this period is that most of the conferences have moved online. So if students are, wishing to get into new stuff without spending too much for traveling and those sort of things, this is the right period to do it, I guess. I remember that you were in Japan for a period, and I don't know, did you learn anything about optimization from Professor Omori or that group over there?
No, actually, yeah, I was in Japan for 3 years because my master is from the University of Tokyo. And so I was in Professor Fujino Sensei's lab. It's called Bridge and Structures. No, my research in Professor Fujino's lab was about bearings, lead rubber bearings, for isolation. So it was mostly focused on seismic effects on these bearings. And it was a structural engineering master. And I was there for 2 years for the master and then 1 year as a researcher before moving to the US. But no, I wasn't aware. Like I said, I started looking into optimization only after joining SOM. Before that, it was different topics, right? I mean, yeah, I wasn't aware of this.
Okay. Well, that's good. I mean, the same applies to also when I started. I wasn't really aware of optimization when I started. There were not courses on that.
Yeah.
It comes after. We have another question about topology optimization, which I guess you'll be able to respond quickly. Do you start topology? Do you start to optimize structural topology by having an idea of the material used, or that's something that is generally applied afterwards? So do you start with geometry, or materials are already taken into account at the very beginning conceptual stage?
No, I think usually when you optimize, is agnostic of material. You just start because it's a geometry problem, right? So first figure out your geometry problem. The one thing you can obviously, that's the first answer. See, because you also want to be free of constraints, right? I mean, you want to start with the least number of constraints you can. Hopefully, it's just a blank sheet of paper, like I said, and you get complete freedom, right? Because as the more constraints you put on your problem, the more your design space reduces into something smaller and smaller, right?
Yeah.
And then look at the solution, right? These are tools for explorations, and there's a lot of parameters involved. And so you need to just explore all those, the design space really, with all those parameters. And at some point you could ask yourself the question, okay, this is the solution. If I don't put any constraint or any thinking about material, guess what? Say that you want to do it in concrete, you could put, a constraint where there cannot be any tension anywhere in your system. Obviously, the solution is going to be very different, right?
Yeah.
It's just, it's explore things and see what happens, because it's important also because you kind of educate your intuition. You develop an intuition for how things should be. And if you see something that doesn't look right, it's because you develop that intuition of what's optimal.
Great. We have another question from a student at Cal Poly. They really loved your presentation as well, and there's particularly the tribute to Guastavino. But this question, I think, is going to be a difficult one to answer. How do you see robots especially, but also optimization software or parametric software in general, getting more and more integrated into the structural engineering industry? What's the timeline, or how do you feel about them?
Well, I think in a lot of the larger design firm, there's already a lot of computational design that is part of the workflow. I think there's a lot of automation already in place in order to streamline, the work processes. It's inevitable. So I think the industry, I would argue that, our industry is trying to move at a faster pace in order to be able to incorporate all these considerations into the design. There is more and more pressure, to avoid to maximize efficiency of system, because it all relates to cost, it all relates to sustainability, right? So I think there has been a lot of effort to incorporate these new technologies. And like I said, the bigger firms, they have specialized groups sometimes, right? TT or ARUP, they have very specialized teams that really focus on all these technologies and incorporating research findings and developing even software in order to be able to have more streamlined workflow. So I think we are trying to be at the same pace with the universities, basically, in terms of researches. And I see more and more collaboration and more cross collaboration. And talking about timing, one advantage, of being on doing research on the industry side is that, we set ourselves with deadlines, but the deadlines is really a deadline, meaning you have to deliver something no matter what. So for example, for the glass vault, we said, okay, this is the opening day. We need to be ready for that. So no matter, despite all the failures, not failures, but all the mishaps and, all the developments, all the technical issues, we still had to deliver something. And that really pushed us to, refine and really work at the problem until we figured out the solution, right? So we really have a very compact timeline, and we really need to, implement something in a very, in a very systematic way and in a very timely fashion. So that's one of the advantages of doing research in the industry.
Yeah. We have another comment for you. Fantastic presentation. Thank you so much. Insightful and inspiring. From Piccolo. I don't know whether that's from San Francisco from here. But we have an architectural designer working in Sydney from San Francisco. He has a question. It's about how does having an architectural team and a structural team in the same office versus having an office that doesn't integrate both themes. So of course, there are benefits in having both themes in the same office. Probably if you could
Yeah, I mean,
comment on that.
yeah, I can comment. Well, and it goes back, in some of the beginning slides, right? I show Fazlur Khan and Bruce Graham, right? So it's kind of in the DNA of SOM to be, to have always an architect and an engineer in a project. It doesn't always happen, For example, the architects may work with other engineers. Like occasionally, we work with other architects or artists, for that matter. I think that the greatest advantage is that we can, from the very beginning, just you sit down with your colleague and you tackle the problem from both angles, architectural and structural. And we kind of go back and forth. I mean, we do design charrettes, and everyone, it could be architect or engineer, can come up with a great idea. And that's a great advantage because I can all, well, not now, but when I was in the office, when we all were in the office, you could walk by your colleague and just say, hey, just show them a sketch, right? Hey, what do you think about this idea, right? Or you keep working on a problem, you think about it, it doesn't have to be intentional, or at least it didn't used to be very intentional, where you need to set up a time to meet with someone to discuss something, right? And inspiration could come across and meet someone on the, in the kitchen, in the office, and say, hey, by the way, did you think about this or that? I think, honestly, I experienced only SOM. Since I've been working, I've only worked at SOM. So I'm not as familiar what it means for, to when it was disjointed, but I can still definitely the advantage of being together for us, because it just brings up those synergies, right? And like I said, it's surprising how an architect could have structural insight and how an engineer could have an architectural insight, right? Because you bring a fresh perspective to the other discipline, right? You look with a different set of eyes, or you have a different way of looking at things. And maybe you're looking at the same problem, but completely different angle.
Yeah. I mean, that collaboration between Graham and Fazlur Khan, it's always fascinating me, even if all I know about it is from what I read in books.
Yeah.
But it sounds like that's still the overall philosophy of the office. I think we're done with the questions here. So we're very well done, Alessandro. I really enjoyed the presentation, and catching up after a few years. I think most of our attendees have also enjoyed the presentation very much, and this strength and this relationship between architecture and engineering that was reinforced throughout the presentation. So it was really great to hear your presentation today. I want to thank you once again for your availability. It's already night for you. I know you're very busy, but it's still very energetic to deliver this presentation. So I'll thanks again, and I'll say goodbye. I'll have to advertise the forthcoming events we have just before drawing this to a close. So,
all right, thank you. I'd like to
thank you once again, Alessandro.
It was a pleasure talking to you all.
So we have other forthcoming events for MSD at home. The next one is scheduled for Thursday, the 22nd of October with Michael Shu, and it's hosted by Piyush Tiwari. The next event will be again on Thursday, the 22nd of October. It's going to be about Danish housing, and it's going to be hosted by Alan Perth. The next event will be on Thursday, the 29th of October at 12 until 1:30 p.m., same time slot as today, with Charles Waldheim. And it's going to be hosted by Leire Asensio and David Ma. And the last one of the bunch, he will be on Wednesday, the 29th of October with Jane Rendell about recent cultural projects at Zadi the Architects, and it will be hosted by our director of the Bachelor of Design, Hélène Frichot. So if you want to rewatch this event or also catch up with previous events we had for the MSD at Home webinar series, you can go on the website you find at this link, where you'll be able to rewatch all of them. So thank you all for attending this webinar. I'll say goodbye now. Have a good day for all of you attending from Australia, and good night for the guys attending from the United States or other parts of the world. Thank you very much. Bye.